My main goal is to tell you a little bit about what parametric equations are, and then how to generate they define a curve in the plane, parametric equations, and I want to show you how to graph that curve with an algebraic technique called eliminating the parameter. So these two bullet points you're looking at are kind of our goals for the lecture. Understand what parametric equations are, and given a set of parametric equations, how do we graph them? How do we graph them? By eliminating the parameter. All right. So let's do a little board work here. Let's hope you can see the board. I know the lighting's not that great. I'm working on other solutions for this, so these things will get better. But what are parametric equations? You're sort of used to thinking about curves in the XY plane. The old idea, the Y variable was given explicitly as a function of the X variable. So in other words, when you drew pictures in the plane, we had two axes. One of those axes represents the inputs, right? The horizontal axis, the X's. And those inputs, when ran through the function, determine the Y value. So the Y value is explicitly determined by the X value. And that's kind of how we thought about all of our functions in these courses so far. Let's see if I can make the light a little bit better. I don't know. I'm not very happy with it, but I'm just going to go with it. Okay, so what's a new idea? This comes up in a lot of contexts. I'll try to convince you that's true, but as a new idea, instead of having these two variables, X and Y, one determine the other, sometimes in many contexts, both of those variables are determined by some third variable, T, I'm going to call it here on the board, where T is the parameter. The variable T, I'll use it a lot in a lot of contexts. It stands for time. It doesn't have to, but it can. So we're still drawing a picture in the XY plane. That's our goal, except we're not going to be given an expression that gives us Y directly in terms of X. Instead, we're going to be given two expressions, X and Y. They both depend on T, and those two expressions are called parametric equations. Yeah, if you see, can you see it if I write it up here? So these two things together are the parametric equations. I'll just erase that label and save the space. And T, or whatever the variable is called, is the parameter. The parameter is determining the X and the Y coordinate in our picture. All right, so let's look at an example. What do I have to give you to generate an example? I have to give you two functions of the parameter. My first one, X of T, is going to be the square root of T. Y will just be T itself. And here, I think I'll specify, well, because I'm taking square roots, that T should be greater than or equal to 0. So these are my parametric equations, square root of T, T is greater than or equal to 0. And the question is, well, what's the graph? Right, that's the question. What's the graph of this thing? Well, I want to show you an algebraic technique. That's this eliminate the parameter. But you know, we can talk ourselves into what this graph looks like by just kind of looking at the parametric equations. We specified that T is greater than 0, so Y will be greater than 0. Square root of a positive number is also positive. So the graph is going to be in the first quadrant. X and Y are both positive. And in fact, as T is bigger, both X and Y get bigger, but Y is going to get bigger a little faster than X because Y is equal to T and X is kind of behind it. It's the square root of T. Square root of a number bigger than 1 is less than the number. So I can kind of visualize what that looks like. The graph is over here. I'm not trying to actually draw it, but X and Y both get bigger and Y gets bigger a little faster than X. It's not a completely unreasonable picture of it. Here, let me switch over to something. I'll show you a better picture I've got ready for you. And we're going to be used to drawing a lot of pictures like this. So let me kind of narrate them for you. You're looking at 3 pictures, hopefully. And so it's important to label the axes. Let's start left to right. So in this first one, the horizontal axis is t, it's the parameter. The vertical axis is x. That takes to get a little used to, but that's just a graph of the first parametric equation. That's the square root of t. It looks familiar. The one in the middle, well, that's t and y. That's just y equals t. So these are the graphs of the 2 parametric equations separately. And then that picture on the right is the graph that they generate. It's in the xy plane. Look at the axes. And it's a better picture than what I just scribbled on the whiteboard that's still behind me. But it has those characteristics. X and y are both greater than or equal to 0. And y is getting bigger as x gets bigger. As t gets bigger. Y gets bigger faster. All right. So now I want to come back and kind of try to answer the question, well, how can we find the old way, the explicit equation that describes this curve? Maybe you have a guess of what you think that curve looks like. But that's what I want to do. I want to describe it with an equation. All right. I need to make some room. I don't have a ton of room here on this dimly lit whiteboard. Let's see how many erases. Thinking there, I didn't have to erase my example, but it won't take me so long to rewrite it, so no big deal. Okay, so what do we got? We have x is equal to the square root of t, y is equal to t was greater than or equal to 0. I'm going to show you something that's called eliminating the parameter. How do we eliminate the parameter? Well, basically, you take one of the 2 equations and solve it for the parameter. Which one? Well, it will depend on what the equations look like. Here, I certainly think it's easier to solve the second equation for t than it is the first one. So I solved one of the equations for the parameter, t equals y. Okay, then I take that information and I replace it into the other equation. Once I've solved for t, everywhere I see a t in the other equation, here there's just one place, I put that in. T is equal to y. So if x is the square root of t, then x is the square root of y. And then in the old way, we're used to solving these things for y in terms of x, so if it doesn't come right out that way, you do it. I'm going to just square both sides. So I get that y is equal to x squared, or x squared is equal to y. And that's a familiar looking equation to me. I'm much more used to thinking about explicit equations like this. It's a parabola, that graph that we were just looking at. You can go back in the video and look at it again. That black curve that was on the right, it's the parabola. In fact, it's the parabola y equals x squared. All right, nice. Let's look at a second example. Let me just flip to it real quick here. Oops. You can start jotting this down. I'll make some room on this board. I want to try to look at the graph. It's defined by those parametric equations. Looks like it says that x is equal to t squared minus 2t. Y is equal to t plus 1. We're not told anything about t, so I'm going to write it on the whiteboard. When that's the case, we'll just assume it can be any real number. All right? I'll come back real quick, but I want to share another picture. I want to just look at the graphs first this time, being a little greedy. So hopefully that's within view for you there. And you can see the equation. I'll just read them left to right. This is the graph of x. I can see on the axes, the parameter is t. The y value, the vertical variable, sorry, is x. So that's a graph of t squared minus 2t. Looks reasonable, parabola with intercepts at 0 and 2. Here's the graph for the y equation. It's y equals t plus 1. It's a line. And over here, I've drawn the parametric curve. All right, so we want to try to understand why did these 2 parametric equations give that curve? Well, I mean, qualitatively, if we think about x. As t increases, x is a positive number that gets smaller, and then it becomes negative, and then it becomes positive again. Well, look at the x coordinates on this curve. That's true. They're positive numbers that are getting smaller. Right there, x became negative if you're watching the cursor. I hope you're watching the cursor. And now x is 0, and it becomes positive and gets bigger again. So this red curve on the far left is just telling me what's happening to the x coordinate in the picture in the far right. It was big, it got smaller, it was negative, it got big again. The middle picture, the blue line, tells me about y. Again, reading the function left to right, I always should. Y was negative, and then it became positive. It's just getting bigger the whole time. All right, so that's consistent with this picture here. Y is negative, right there. Watch the cursor, y became 0. Now it's positive, and it stays positive, just getting bigger and bigger. In fact, the way I'm tracing this curve, and I'm going to write this when we come back on the whiteboard, the parametric equations don't just define a curve, they give it a direction. The cursor is moving along the curve in the direction x comma y would as the parameter increases. All right? So let's see if we can't come back to the whiteboard and find an equation for that curve. It also kind of looks like a parabola to me. Okay, so let's see. I've got the equations all prepped here. So I'm going to eliminate the parameter. This is our second time through. So looking at the two equations, it looks like it's easiest to solve the second equation for the parameter. So I'm going to take the y equals t plus 1 and solve it for t. I would get that t is y minus 1. And then in the top equation, the x equation, everywhere I see a t, I'm going to replace it with the quantity y minus 1. All right, so let's see if I can try to write it neatly. X is, well, I have to take y minus 1 and square it to subtract 2 times y minus 1. All right, you can pause the video now or just fast forward it, because for a second here, I'm just going to jostle this thing around and do some algebra. I think I'll lean down to try to make the handwriting better. I hope you can see one more line. I'm going to try to be a little clever here. Factor out a y minus 1. Maybe that's as low as I should go there. So coming back up here, I would get that x is y minus 1 times y minus 3. Yeah, and I can recognize that is a parabola. I just try to make a crude sketch of what we were just looking at. And it crosses the y, it's a sideways parabola. It has y-intercepts at 1 and 3. So we learned a little bit more about that picture. And I'll just draw it sort of like we did on the screen. And then one more comment. So that's the explicit equation. I'm going to leave it solved for x because it's not a function of y. It's not a function of x. It's a sideways parabola. But what we were talking about on the screen, as t increases, we're always going to label these parametric curves, as we'll call them, with direction arrows. The direction indicates the direction that you would move along the curve as the parameter increases. So like we were talking about before, as t goes from minus infinity to infinity, this first equation, say the x equation, that parabola we were looking at, it's harder to see it in this form. So go back in the video if you need to. I'm thinking about that red graph. That red graph told me that x was going to be big and positive, be negative for a little bit, and then be big and positive again. The whole time, y was just getting bigger. So that's how I know that the curve is directed like that. So if you have questions about that, write them in the comments in the discussion page, or bring it up in office hour, because when we graph a parametric curve, I always want to include the direction that it's, I'll usually say the direction it's swept out or traversed. You can tell by my language, I like to think of t as time. And I like to think that these functions, x and y, are together telling me where something is. So I personally like the context that this is like the path of motion of something. At time t, these two functions tell me where it is in the xy plane. And in that context, I like these direction arrows because it tells me which way it was moving. All right, good. So I want to do one more example. This video is getting a little bit long, but maybe you've already taken a break. Let's check out one more. I'm going to just put it up on a slide while I erase the board to save a little time for you. One more example. This time our parametric equations. Given by the trigonometric functions sine and cosine. Here, the domain on the parameter t was specified. We're looking at t between 0 and 2 pi. Okay, so I've almost got these things written down. And maybe you're already thinking, you know, solving one of these equations for t doesn't look so algebraically pleasant. Let's move over and look at the picture real quick before we talk about the algebra. This time, I don't want to show you the black curve yet. Here I'm graphing x and y. Look carefully at the axes. Horizontals are t's. Left pictures x, right pictures y. I've been consistent about that and the colors. Let's see if we can, what the thing's doing. As t goes from 0 to 2 pi, well, the x-coordinate starts off at 1, drops down to -1, and it climbs back up to 1. And while it's doing that, the y-coordinate climbs from 0 to 1, falls down to -1, and then climbs back to 0. So it's not so easy to imagine. If we plotted some points, kind of choosing, you know, equally spaced t values, we could start getting a picture. But maybe you have it in your mind, maybe not. It's not so obvious. Let's see if I can put all three on the screen at the same time, but it would end up looking something like that. It ends up looking, let's see if it's consistent while I can mouse over it. Here, x is 1, y is 0. It's consistent. At time 0, x is 1, y is 0. And then as time starts, quote unquote, x starts getting smaller while y gets bigger. But the biggest y we'll get is 1. X is 0, y is 1. On these curves, we're here and here now. Yeah. And so on. Now y is smaller, x is -1. Okay. It's important as you're reading this section, one of the skills you're trying to develop is how these two pictures together can be assembled to produce the picture in the XY plane. But it's not easy. It takes a lot of examples because your brain's assimilating a large amount of information when you're doing that. Okay, so let's end this by how do we eliminate it? How do we find it? Looked like a circle. The black thing looked like a circle. How do we show that it is or isn't one? When sine and cosine are involved, we're not going to eliminate the parameter by solving one of these equations for t. You can, but it's sort of a mess. Instead, we're going to take advantage of a trig identity. A trig identity that you will recall because we did a lot of it in our trigonometric substitution. If I square both of these equations, so if x is cosine, well, x squared is cosine squared, same for y. And if I add them together, well, I get cosine squared plus sine squared, but cosine squared plus sine squared is 1. So we've eliminated the parameter not by solving for t. It's a different method. We did it by taking advantage of some identity. And with sines and cosines, I always want to try to take advantage of this identity. Okay? So, well, you recognize that. That's the equation of a circle. Its center is at the origin and its radius is 1. It's exactly what we were just looking at. And when we were looking at it on the screen, as t increases, you can think of t in this example, if you like, as the angle. That circle will be traversed counterclockwise. Okay, well, so now in this module, as we're going to call them, it's time for you to look at the handout that I've got on Canvas, complete it and upload it to me or email it to me. Send me a picture of it or a PDF. And the homework in the book that's also posted on Canvas. Do those problems. You can look at Slater for solutions. You can talk to me about it. Maybe I'll see you in an office hour. And yeah, I hope these videos will get better. I think they will.